Right. So on the problem set, Newton's second law equation. This is a second law equation derived from a physical situation, and we are going to look at this in relation to what we just talked about, which is inclined planes. So right away, what information do we know?
A is 0.
A is 0. So that means what?
We are not accelerating.
We're not accelerating. So we're moving at a constant velocity.
That's a conscious thought.
It does. It does. It takes serious thought to remember that. You're not accelerating. So is it moving?
Maybe.
It could be, but not necessarily,
Not
right?
enough information given.
That's right. Remember, these forces don't tell us about velocity. Forces tell us about how velocity is changing. No, not yet. You need more information.
Yeah.
You need distances or times, and then you can tell about velocities. What is this guy? What is this guy over here? This 57.
That's the normal force. Normal force.
Is it a normal force?
No.
It's a force in the x direction.
It's the way that it's moving. It's the force that's acting upon it. It's just the force that's acting on it. And which direction is it acting flat, or is it acting at an angle?
It's an angle. I have a question. Why are they factoring in?
Andrew. What's your
Why
question?
are they factoring in n if n would be perpendicular to this force?
We're gonna get there. Where do you see n? Where do you see normal force?
Kilograms multiplied by
That piece right there. Is that it?
That piece. How do you know that it's normal force?
Oh, because it's multiplied by the
Because it's multiplied by the coefficient. So if that's the coefficient, then this thing must be normal force. Good. This thing we've identified is just a push. What is that guy over there with the sign?
force.
Yeah, right. That's mg sine of theta, which we identified as the force down the plane. So if we're talking about friction and a force down the plane, and then maybe a push, are we talking about an x direction or a y direction? X. We're talking about an x direction. We've got mg sine of theta, so what does that tell us about the surface? It's on an incline. That's the only way we get these cosine and sines in there. There is a way to get a cosine or a sine in there on a flat surface. How might we do that? If you push or pull it at an angle, right. But we know that this is an incline because there are two factors, both sine and cosine. That wouldn't happen if we're pulling at an angle, or can it happen? Normal force tells us. Is normal force always mg on a flat surface? What about when you're pulling at an angle? What's normal force?
reduced.
Mg minus something. It wouldn't just be mg times an angle. It'd be mg minus some m force at an angle, right? But the fact that this is mg at an angle tells us that we're on an incline. So this little piece here is mg cos theta. So drawing out this situation, we've got an incline and a mass on an incline. What is the mass of that mass? 14 kg from both of that. So that's 14 kilograms. What's the angle? 18-degree angle. Which gravity's 9.8. So we're on Earth.
Not minus.
Clever fellow. Which way is this thing going? It's not accelerating, but let's say it was moving.
It is moving. Is it moving up the incline?
Let's suppose that it's moving. Which way would it be moving?
Up.
How do you know up the incline?
Oh, yes.
Excellent. This is pushed. This is saying mg sine of theta is this way. So mg sine of theta is in this direction. Which way is it being pushed? That way, because this sign is different than this sign. Now, does that tell you you're going up the plane?
We're not accelerating. It's 0.
Can you be accelerating down the plane in this situation? Or not accelerating down the plane in this situation?
Yes, you could be.
Sure. We actually can't tell which way we're going.
Oh, trick question.
Trick question. This doesn't tell us the direction of that constant velocity. The only way to be able to tell direction is if we were accelerating. Because I can be pushing up and sliding down. If you've ever moved like a piece of furniture up a ramp or down the ramp, you have that experience. Hopefully you're not on that side because it's a little bit dangerous, but you're pushing up so that the thing doesn't crush you, right? Or you don't want it to accelerate down the ramp, so you're pushing up and backing up.
Push on it so it doesn't kill you.
Normal force is in this direction, mg straight down. So we have this piece, mg cos theta, and we have this piece, mg sine of theta. And that's mg sine of theta. There's mg cosine of theta. There's the push. Sorry, too many lines, right?
Yeah. You lost me after that thing.
Right. You see that these are cosine and sine. You okay with that idea? We're just kind of explaining where all these things come from.
Now I follow you.
All right. The normal force is mg cos theta. That's where this is in the equation. Mu times the normal force, mg cos theta. This incline, or this gravitational force, is what's pulling us down the plane here. So we don't have to have both of these on there, right? This thing is that thing. It's the same. Mg sine of theta is what is trying to accelerate us down the plane. That's over here. And then Fp is in the other direction to mg sine of theta. So Fp has to be up the plane because mg sine of theta is always down. Sorry. It's just saying that this is the opposite of this.
Is it possible for it to be like 57 plus the friction stuff because the gravitational force pulling it down is greater than the force pushing it up the plane? Wouldn't the friction swap sides somehow? So that is pulling against, it's just trying to like pull against the gravity down, or against like.
So I think I see where you're going with that. This is, I think I misspoke earlier. This is definitely going up the plane because friction is acting in the same direction as mg sine of theta, which is down that way. And friction would only go down that way if we were moving up. So that's, yeah, you're exactly right. This has to be moving up. If we were pushing it that way, but it was moving down, friction would be acting in the same direction as the push. That's right. Good. Very good. Yeah, thank you. Excellent.
Wow, 2 days in a row. You really should let it.